Today, Tyler and Taylor's group and Will's group investigated this relationship where a class starts out with 10 mealworms for an experiment. The population doubles, which means it grows by 100% every month. So they determined how many mealworms the class will have for their experiment in 3 months and I think even in a year. But first they started with a function. So they started with this function f at x equals 10 times 2 to the power of x. They reminded us that f at x in this case is going to stand for the number of mealworms after x months. And they picked 10 because that was the starting number of mealworms. Also, they had an increasing amount of 100%. So 100% is 100% plus 100%. That turns out to be 200%, which is 2 as a decimal. And so that's why they were able to write 2 in as their power. So again, they're using the function f at x equals a times b to the power of x as their generic exponential function. So you can see here is where they actually substituted in to calculate the value for 3 months. So we're just going to zoom in here. So when x is 3, then they put in this value 3 as an exponent and took 10 times 2 to the power of 3. BEDMAS tells us we need to evaluate 2 to the power of 3 first, so they got 8, then multiplied it by 10, so there's going to be 80 mealworms after 3 months. We also knew that we needed to figure it out for 12 months or for a year, so they substituted in x, the number of months, as 12, did the calculation, and came up with the fact that there's going to be 40,960 mealworms after 12 months. Now, since their calculation was done quickly, it was recommended that they changed either the growing time or the number of months it required to double. So they actually set up a second version here where the worm population is increasing by 75% each month, not 100%. So they still have, and they're going to start with 20 worms this time. So starting with 20 worms but increasing by 70% means that they have 1.7 as their common multiplier, the 1 for the original 100%, the 0.75 for 75% growth, and power of x for the number of months. So that was nicely explained. And then they decided to calculate how many mealworms there would be after 4 months and after 10 months. So again, they substituted in x, showing nice function notation, and determined after 4 months there would be only 188 mealworms. After 10 months, there would be 5,388 mealworms. So Jacob, Anna, and Aaron's group had this question about termites on the porch. There are 8,000 termites, and they are putting on a treatment that will kill 40% of the termites every day. So they needed to come up with a function to answer the questions for how long for 3 days as well as for 36 hours. They didn't quite show all their work for 36 hours, but we'll discuss that in a minute. First of all, they nicely described that f of x is going to stand for the termites remaining, because that's what they were talking about, how many will be there at the end. And they also said that x is going to be the number of days passed. So they knew they started with 80,000 termites, and that they were losing 40% per day. So first they actually investigated the relationship to see if they understood how it was working. So they took 40% of 800,000 and found out that that was 320,000. So that would be the amount that they lost, which means that there would be 480,000 remaining. Then they figured out the next day, so this is 1 day later. They again figured out 40% and removed it. So we continue to see this decline. And we see that we are losing different amounts each time because there's a different value that the 40% is being taken from. So they decided to write the function, and they had 80,000 because that's the starting value, but they also included the value of 0.6. Now 0.6 is a little bit odd. So 0.6 is 60% written as a decimal. So why would they have 60% instead of 40%? Well, again, the value was we were killing 40%. So 60% is remaining, and we want to know how many termites are remaining. So then zooming in on the function, they decided to give this a test that was 80,000 times 0.6 to the power of 1, because they actually already knew that after 1 day, there should be 480,000 remaining. So when they put this into their calculator and used the function, they found out their function is working properly. So that's nice. So then the answer to question A, which is how many remain after 3 days, they replaced x with 3 and did the calculation to find out that there's 172,800 remaining, which still matches with their original sort of playing around with the idea. However, they had to expand on their idea in order to answer B, because B was asking about 36 hours. Now, it's not shown here, but they decided that x would be 1.5, and that's because 36 hours is actually the same as 1.5 days, and the x value had been defined as x is talking about days. Lastly, in our summary here, we had started off while we were summarizing on the board. We're going to use the exponential function generally, and we looked at if there was a growth or if there was a decay. So we had a declining curve if there was a decay. We managed to point out that if we have a 5% decay or decline, that would be 0.05 as a decimal, but that really means there's 0.95 left. And so the 0.95 left is the B value that you're after. Okay? So that matches up then with the things that Mackenzie and her group had decided, and that was that when you have a decay, your B value would be less than 100%. So in other words, you will have less than 1. So some examples that we saw today, the one we just looked at was 800,000 times 0.6 to the x. This was a decay because it was killing off 40%. An example of growth that we saw was like Tyler and Taylor and Will's group, where they had written functions where it started and then it was doubling every month. So they wrote a function more along these lines. And again, that holds that if it's more than 100%, the B value will be bigger than 1. So in other words, here we are, the B value is bigger than 1. We had a nice growth curve. There's an example then. This one should actually be under the decay section. And it is a sample of the calculation that we might use to determine the number of items remaining after 1 day or 1 cycle or whatever we're measuring. So there's your summary.